All right, so today we're going to talk in our second lecture about point groups. Just let me set out a few things. All right. So can anyone remind me about the 10 different kinds of symmetry elements that we discussed in the previous lecture? So I'll just write them down.
Sir, 1, 2, 3, 4, 6. M.
Mariam,
Which was
Mariam, just a minute. Sorry, just a
sure.
minute, please. All right. So they are 1, 2,
3,
3,
4,
and
6,
6. So these
and
are
M
cyclic operations. M, which is
is also 2 bar,
2 bar.
and then there's 3 bar,
There's
4
also 1 bar.
bar,
Let's go in order.
also
There's
1
1
bar,
bar as well. Then there are 3 bar. There's
4 bar,
3
and 6
bar,
bar.
4 bar, and 6 bar. So there are 10 symmetry elements in total, and most of them are involve the definition of a point or an axis. So these elements, these symmetry elements, they generally deal with rotation. In fact, all of them involve a rotation. All right. So 2 is a two-fold rotation, 3 is a three-fold rotation. Likewise, 6 bar is a six-fold rotation followed by an inversion operation. 1 bar is a one-fold rotation. That is, you do nothing and then do an inversion. All of these uh, symmetry elements, they involve a rotation of one kind or the other. Now, what we could do, in fact, is we could lump these rotations together. Has Does anyone remember or has anyone studied group theory? And can anyone tell me what is a mathematical group?
Sir, it's a kind of set with
Mhm.
closure under multiplication, associativity, and some other. I think there are two more properties. I can't remember precisely.
चाहे आइडेंटिटी भी होनी
Mhm.
चाहिए और मल्टीप्लिकेटिव इन्वर्सेस भी होने चाहिए
हाँ, मल्टीप्लिकेटिव का तो नहीं पता, लेकिन इन्वर्सेस होने चाहिए. So there has to be an inverse, there has to be an identity. You concatenate two operations. The new operation should also be a member of the group, and then there is associativity as well. So these are properties of a group. So it's a set of operations, a set of elements, a set of objects which has these four properties. Now we can lump these 10 symmetry elements together and form groups. And these groups are called point groups.
हम सर जन से हमने ऊपर ऑपरेशंस लिखे हैं इनमें रोटेशंस हैं और इन्वर्जन्स हैं तो हमने रिफ्लेक्शंस भी तो पढ़े थे
तो एक ही तरह का रिफ्लेक्शन है ना, 2 बार अभी हमने पढ़ा है. तो 2 बार is a two-fold rotation followed by an inversion.
तो
Okay.
that sort of counts as reflection as well because when हम
This is
invert करते
reflection.
हैं
This
ना
is tantamount. This is the same as reflection about a mirror plane. Yes.
हाँ yes you discussed this last time okay sir
Now let's look at the point groups. And when we're talking about crystals in 3 dimensions, it turns out, it turns out that there are only 32 point groups, neither more nor less. So we can construct 32 point groups for our crystals and for our lattices. Crystals are our patterns and lattices are our grids of points. All right, so let's see how we develop these point groups. So this is a really important concept, and not many condensed matter physics courses talk about symmetry in this detail, but I think it's really important to understand the crystalline state itself. And how do we describe the crystalline state? That's why I'm devoting these four or five lectures on discussing the various descriptions of crystals in terms of symmetry. So let's see how we develop the point groups. And notation abounds in this discussion. There's notation everywhere. There is symbolism. There are pretty pictures. There are geometrical constructs that we generally use to describe the symmetry operations. So first of all, the first point group. What's the simplest point group that you can think of? Really, the simplest.
Identity.
Identity, exactly. So number one point group is just the identity. It just has no symmetry whatsoever. This is of course a point group. It satisfies all the properties of a mathematical group. And now if you would like to represent this point group and look at the action of this group on a lattice or on a crystal structure, and you know the difference between a lattice and a crystal structure. A lattice is the skeleton, and when you put flesh on the skeleton, it becomes a crystalline structure. Okay, and the flesh are the atoms here, the molecules here that are studied onto the placeholders, which are defined by the lattice points. Now, one, if I would like to represent one, what I could do, I could draw what is called a stereogram. And let me draw the stereogram for this group. I draw a circle, and just for my visual convenience, I cut it into two halves just for my visual convenience, and I draw a circle. Now the circle is my object. When the operation 1 acts on this object, nothing happens, it remains where it is. So this is the stereogram of the point group 1. Okay, I'm using international notation throughout the Sean Fry's notation, but I will sometimes also uh, I will at the same time also give the old notation, the Herman Manguin notation. So one in the old notation is represented by C1. Now the second group is is the possibility of having a two-fold rotation. But the two-fold rotation comes with an identity always. So every group must have an identity, one. So this is the second point group, that is, it comprises identity and it comprises the nothing, doing nothing. So now if I would like to draw the stereogram for this particular operation, excuse me, I draw my circle, I draw my starting object here. Now suppose that the axis of rotation is through the center of this diagram here. You know that this two-fold rotation can be represented by a pier sign. What this two-fold rotation does is that it takes the object here. Okay. So this is a stereographic representation of the point group, which is generally labeled as 2. Now, 2 is a symbol of the point group itself as well, and it contains the elements 1 and 2. So we're using the same notation for denoting symmetry operations, as well as we're labeling the point groups with the characteristic symbol. And the symbol here for the point group is 2. You would like to make it bold if you want, just to specify that it is the label of a point group. And in the old notation, this is called C2. So we've seen 3 point groups. Similarly, we can form point groups C3, which is 3, C4, which is 4, and C6, which is 6. Okay, and let's draw the stereographic projections for these groups. So I have group number 3, group number 4, and group number 5. So if I were to draw the stereographic projection for 3, for example, you draw a circle. Now I place my starting element here. I have a three-fold rotation about the axis, which is the exact center of this circle, and I end up here. So I do a rotation by 120 degrees and another rotation by 120 degrees. This is my C4, C3 or 3. Uh, what elements does it comprise? Can anyone tell me what elements does this point group comprise of?
1 and 3.
That's it? Is
There
that
will
all?
be
सर 2 भी तो होगा
कौन सा?
सर 2 नहीं होना चाहिए
3 done twice. 3 followed by another 3. That is a
yes
240 degree rotation. Okay, so these
yes
3 elements now form a point group, which is called the point group labeled as 3, and in the old notation labeled as C3. Likewise, I can have C4. A 90-degree rotation lands you here, another 90-degree rotation lands you here, and another 90-degree rotation lands you here. Okay, and I can have C6 as well. So these lines that I'm drawing, they do not represent mirror planes. They merely are a visual guide for me. So I put a element here, it will create an element here at 60 degrees, 120 degrees, 240 degrees, 3, 60, 120, 180, 240, and 300 degrees. Okay. Now, if you look at the elements of this group, I have 1, 6. I have 6 done twice, which is really 3. I have 6 done thrice, which is really a two-fold rotation. And I have 6, 4, 6, 5. So I have 6 elements in here, correct? And I can lump these together. I can find the inverses. So for example, the inverse of 6 would be this operation, right? The inverse of this would be this operation, and so on. So these 5 point groups that I've mentioned, they are examples of cyclic groups. And all crystal structures and lattices can be assigned to one of the 32 point groups, and these are just 5 of them. All right, so any questions here?
I'm sir so we can have groups this can there we have rotations more than the sixth one so can't we like go to
Aslan,
infinite
oh
I'm
no,
sorry
in 3 dimensions, when you have finite points, discrete atoms on 3-dimensional network, these are the only 5 cyclicities that you can have. You cannot have, for example, a 5-fold rotation or a 7-fold rotation. With these symmetry elements, you cannot completely fill up space, and there's a proof for that. Okay, so you will always, for example, with pentagons, you cannot completely fill up a 2-dimensional space. Okay, with hexagons you can. Uh, eh, so you can't do this with pentagons. So I think so. There's a mathematical proof for this. You cannot have a 7-fold rotation. Okay. So anyone wanted to ask another question?
Sir, why didn't we have a 2 square in the two-fold in the second point group?
Because 2 square is just the same as identity. You do a 2-fold rotation twice, you get a 360-degree rotation. It's just the same as identity.
Oh, all right.
Okay, so this one is really 2 square.
Okay.
Answer the inverse of 2.
The inverse of 2 is 2 itself.
Okay.
Now what we could do is the following. We have constructed these 5 point groups. What we would now like to do is, now we would like to add a mirror plane. Now the mirror planes are represented by M, but I'll use a different symbol here. I'll use the symbol sigma for a mirror plane, and put a small h with it. The h represents a mirror plane that is perpendicular to the axis of rotation. So just excuse me for a minute, please. Just excuse me. All right, so the axis of rotation that I mentioned in the 5 cyclic groups, they are principal axes. Okay. And in the stereograms that we've drawn, they're coming out of the plane of the paper. They're projecting outwards. Now let's draw a mirror plane in the horizontal plane. So we're drawing a mirror plane in a plane that is perpendicular to the axis of rotation. Okay. So when we do that, let's look at the different point groups that we can create. Uh, so point group number 6. So in point group number 6, we have a one-fold rotation followed by a mirror plane. Okay, so let's draw the stereogram for this. So this is our object. I do a one-fold rotation, which means I do nothing, and then take a mirror image about the horizontal plane. So an object that is above the mirror plane is reflected below the mirror plane, and we get its chiral enantiomer. We get its mirror image. So I can represent this by splitting this object into two halves. One half is above and the other half is below, and I put a comma sign here. Okay. So this is just a shorthand of representing two objects, and we're looking at them from the top. They are juxtaposed one on top of the other. So one is directly below the other one, and one is the mirror image of the other one. Okay. So this is a shorthand symbol. And now this point group is just a mirror plane. Okay. And is given the symbol M. Okay. All right. So is this making sense here?
Yes, sir.
Okay, good. So now what I would like to do, I would like to go one step further. I would like to do a two-fold rotation followed by a mirror plane, which is perpendicular to the axis of rotation. So can I ask you to draw the stereogram for this? I just take 1 minute and attempt. Unfortunately, I can't see what you've done, but you're welcome to let me know how this is going to pan out. So this is my initial object. It's above the mirror plane. So I don't need to draw the plus and the minus signs with the cyclic groups because they don't leave the plane. But here for mirror planes, which are in the plane of the paper, which are represented generally by this symbol, it's always nice to have objects drawn above and below the mirror plane to show their precise positions. So I'll just give you a minute to try drawing the stereogram for this. जी आप बता सकते हैं कोई कि क्या इसका होगा आंसर?
So we can draw on your screen, वैसे.
जी बताएं. अच्छा, can you? या कम से कम मुझे बता दें, where should I draw a circle? Okay, good. Put a plus or a minus sign. Minus sign. Do you want to put a comma?
So ये काफी मुश्किल है यहाँ
Okay,
से
चलो मैं करता हूँ. ठीक है. इसको अब हो सकता है मैं मिटा भी सकूं. आपको ही मिटाना पड़ेगा, चलें कोई बात नहीं. So I put a circle here with a minus sign and a comma because I do a two-fold rotation. I'm above the plane, then the mirror reflection takes me below the plane. So plus becomes negative and I get a comma as well. So now in this point group, I have a two-fold rotation and I have a mirror plane perpendicular to it. So the symbol for this, the international symbol for this group is 2/m. And whenever I have a forward slash in the international notation, it means that I have a mirror plane perpendicular to the principal axis of rotation. Okay, so this forward slash represents perpendicularity between the mirror plane and the axis of rotation. Okay, so it's very straightforward and systematic. It's like playing a game and learning the rules of the game. Likewise, I can have a, a three-fold rotation followed by a mirror plane. So here I start off with something which is plus. I get something which is negative and an image. Then I get something which is plus without a comma. Then I get something which is negative with a comma. So I split this into half. This becomes plus. So uh, this is a threefold rotation followed by a mirror plane which is perpendicular to the threefold axis of rotation. Now, if you observe this, now we would like to come up with a symbol for this point group. Now, in the old notation, this M is represented by C1H. Okay, one fold rotation and a horizontal mirror plane. This is represented by C2H. This would of course be represented by C3H. Likewise, I will have C4H. I will have C5H. Now, in this C3H, if you'd like to construe or construct the international symbol for this point group. Now, if you observe carefully, if I were to do a six-fold rotation on this object, this plus object, this thing here, I would land up here. And if I were to follow it with the center of inversion operation, an inversion operation about the center here, I would end up here with a negative sign and a comma. And you can do this for all of these points that I've drawn. So this C3H is also equal to a six-fold rotation followed by a center of inversion, 6
Sir,
bar.
can you please explain this again?
Okay. Do you understand the 3H operation that I'm doing a three-fold rotation followed by a mirror image?
Yes, sir. Yes, sir.
But this is the same, I'm arguing that this is the same as a six-fold rotation, a rotation by 60 degrees followed by an inversion. Okay, a roto inversion. And how
Yes,
do
sir.
I, okay, okay, got it. So I have this object here. Let me keep it simple. Positive sign. I do a six-fold rotation. I end up here, positive sign, but then I do an inversion about this point. I end up here. But since it's an inversion, anything that is above goes below. And I put a comma as well because it's an inversion. I need to construct the isomer, the stereoisomer of this, the mirror image of this, because it's an inversion operation. And then I repeat, I do a 60-degree rotation of this point, I end up here. And then I do an inversion about the same point, I will end up here. But then I get something positive because the negative is going to a positive. This is what the inversion operation does. Something that is below goes above. and the comma is commaed again, and the comma is negated in a sense. So likewise, I will construct all of these points that I've drawn. So this point group 3H in the old notation is really represented as 6 bar in the international notation. A threefold rotation and a mirror plane is the same as a six-fold roto inversion operation, in other words. Okay? Likewise, I can have C4H plus 90-degree rotation plus mirror image negative, comma, 90-degree rotation positive without a comma, 90-degree rotation negative with a comma. Okay, I do a 90-degree rotation on here, I get this. Okay, but also I do have a mirror plane as well. So this positive is also being reflected in the mirror plane itself, and I get a comma here. So each one of these has a, so this is the exact stereographic display of the C4H, which is has a symbol, a four-fold rotation followed by a mirror plane that is perpendicular to the principal axis of rotation. This 4 / m is the symbol for this ninth space group. Likewise, I have C6H, which will be 6 bar m, 6 / m. Okay, now I've constructed 10 point groups. The first 5 point groups are the cyclic groups. Okay, Heather, just a minute. The first 5 point groups are the cyclic groups, and the next 5 groups are constructed by the cyclic groups, and then you would like to multiply the cyclic group with this set. Okay, so this is a shorthand notation for the operations that I've done in constructing point groups 6 to 10. That is cyclic operation, n-fold cyclic operation, followed by a mirror rotation, the possibility of a mirror rotation. So I take two elements in a set, which includes the identity and the horizontal mirror reflection, and I concatenate it with the cyclic group, and I construct the 5 new NH
Sir,
group.
sir, do these operations commutate?
Which operations? The mirror and the
Yes, sir.
rotation? Yes,
Yes,
they
sir. आपने वो
commutate.
left. Okay, sir.
Yes, they commutate.
सर ये जो आपने C4H में इनके एंटायरमेंट्स बनाए हैं, ये थोड़ा दोबारा
Hmm?
एक्सप्लेन कर सकते हैं? ये समझ नहीं आई कि ये एंटायरमेंट क्यों बन रहे हैं। जब हमने पहले उसको रोटेशन की 90 डिग्रीज की, उसको रिफ्लेक्ट किया तो वो नीचे चला गया, फिर करके हमने रिफ्लेक्ट किया तो ऊपर आ गया, फिर करके
ठीक है।
रिफ्लेक्ट किया नीचे चला गया, और जब हम दोबारा करेंगे तो इट विल बी अबव उसी एग्जैक्ट पोजीशन पे, उसका एंटायरमेंट ऊपर की तरफ बनेगा या फिर क्या होगा?
देखो, if we have the 4m group, 4/m group, I draw a point above the plane. Now it contains a mirror plane in the horizontal plane. So without any rotation, or just with one fold rotation, which is a member of the C4 group anyway, I need to do a mirror reflection about the same point. So what this does, this object is mirror reflected at the same position. So if something is above, I get something that is below with a comma sign.
ठीक सर, C2H में भी
Okay.
इस तरह नहीं होना चाहिए था फिर?
C2H में भी बिल्कुल, सॉरी, बिल्कुल C2H में भी ऐसे ही होगा, बिल्कुल ठीक, सॉरी, बिल्कुल ठीक, आई फॉरगॉट, बिल्कुल ठीक. All right, so now we've constructed 10 point groups. We have the cyclic groups, and we have the groups which are formed by the concatenation of the mirror plane, which is perpendicular to the principal axis of rotation. Now, similarly, we can construct 4 new groups. And those new groups can be constructed by taking the cyclic groups and concatenating them with vertical mirror planes, 1 sigma v. Now, why are there 4 new point groups, not 5? Okay, so let's investigate these point groups. Our
Sir,
first
I had my
candidate is
hand raised.
G
Sir, I
Heather.
had a question. Sir, in some cases, you wrote negative sign and the comma towards the right, and the plus sign in the left, and in the other cases, it's the opposite. So, sir,
It doesn't matter
C.
whether it's right or left. It doesn't matter whether it's right or left. They're at the same position, so I could do either.
All right, ठीक है, sir. Thank you.
Okay. Now what I would like to do, let's take the point group 1, excuse me, point group 1 and have a vertical mirror plane. So 1 followed by sigma v. So now I'm drawing a vertical mirror plane by a line. So this is my vertical mirror plane coming out. Okay. Now if I have now object here above, it will create an object here which is above but the mirror image, right? Is that agreeable?
Yes, sir.
Yeah. But how is this different from a simple mirror operation? It's really no difference. It's just a horizontal mirror plane is becoming a vertical mirror plane. It's just a choice of directionality. Okay. So this point group has the identity operation and a mirror plane. This point group also has the identity operation and a mirror plane. There's no difference between these groups. So we so having a one-fold rotation followed by a vertical mirror plane is the same as having a one-fold rotation and a horizontal mirror plane. Okay, the elements of the group are the same. So we have not created a new group here. So this is not a new point group. That's why we cannot construct 5 point groups by adding a vertical mirror plane. Rather, we can construct 4 point groups.
सर बट इन दोनों की इमेजेस डिफरेंट नहीं है. इसमें वो सर्कल बिल्कुल उसके सामने है, लेकिन वहां पे तो
But
उसके
you
ऊपर
look at,
ही.
so if you take this circle and rotate it by 90 degrees and look at from the other side, it's the same as the original. So we have to look at the elements of the point group. The groups are totally identical. There's nothing new in this group. Okay. The groups are equal, mathematically equal. Okay.
All
So
right,
it's
sir.
nothing new. Now what we could do is we could create point groups, which I've labeled in this. We could have a two-fold rotation followed by a vertical mirror plane. So let's draw the stereogram for this. My initial object, a two-fold rotation comes here. And when I have a two-fold rotation that comes here, it goes here, minus with the comma. Okay. But the mirror plane itself creates this. And this would create this. All right. So here are my mirror planes. This is one mirror plane, which I started off with. The two-fold rotation axis is also here. And now I have a vertical mirror plane. The vertical mirror planes are drawn by solid lines, by the way, which I've drawn in red over here. All right. So now if you observe, what we are having here is a two-fold axis of rotation and a vertical mirror plane. The vertical mirror plane contains the principal axis of rotation. But when we've generated this stereogram, we observe that automatically a new mirror plane has been created, and this is this mirror plane. Another vertical mirror plane has been created because this object here, this object here is now the mirror image of this object here.
सर हमारे जो एंटायर्स हैं इनको ऊपर ही नहीं होना चाहिए प्लेन, क्योंकि हम इसको
सॉरी
सिंपली
सारे
वर्टिकल।
ऊपर, सॉरी बिल्कुल सारे ऊपर हैं, आई एम सॉरी, all of them are above, all of them are above because these are vertical mirror planes. So this mirror plane that I've drawn over here is automatically created, this one. I started off with one mirror plane and a two-fold axis of rotation, and an extra mirror plane has been created. All right. So this is characteristic of when we deal with symmetry elements. You put two symmetry elements together, a third symmetry element is created, or a fourth symmetry element is created. This point group in the international rotation is represented as 2mm. A two-fold rotation and two mirror planes, mm. And the old notation, it's C2V. Okay, and there is no forward slash sign because now the mirror planes contain the principal axis of rotation. They're not perpendicular to it. Likewise, I can generate C3V, which is 3m. I can generate C4V, which is 4mm. I can generate C6V, which is 6mm. And you would like to draw the stereograms as a homework. Okay, let me do C4V for your convenience. So here I go. Object, 90 degrees rotation, followed by a vertical mirror plane. And up here, everything is positive. 90-degree rotation, followed by a mirror operation. I end up here. 90-degree rotation, okay. So now this mirror plane creates this object, this mirror plane creates this object, this mirror plane creates this object, this mirror plane creates this object. And these are my mirror planes which go together. They are in synchrony with one another. They have to be together. I have a four-fold axis of rotation.
सर जौन से
Here at the
लास्ट वाला
center.
सर्कल है उसमें कॉमा दूसरे वाले सर्कल में नहीं आएगा?
ठीक है?
Yes sir.
Okay, so I have a four-fold axis of rotation and two mirror planes. All right, now I could draw the stereogram for 3m. I could draw the stereogram for 6m, 6v, 6mm. So this makes 14 point groups. Now we could also have roto inversions. So I can have a point group which is simply one bar. So a 360-degree rotation followed by an inversion about the center. Okay. So this is one bar. An improper rotation or a roto inversion. The old notation gives it the symbol S1. 2 bar we've already seen is the same as a mirror rotation, so it's not a new point group. However, 3 bar is a new point group.
सिंस हमने रोटो इन्वर्जन किया उसमें ऊपर वाले सर्कल के साथ माइनस साइन क्यों आ गया?
कौन सा वाला?
ये सिंस
क्योंकि
हमने अभी आखिरी वाला किया.
something, so if I look at it from the side here, if I look at this from the side here, this is my point A. Let's call this point A. An object that is above, when I reflect this, or sorry, invert this object above the center of symmetry, it gives me a point below. And it's a mirror image as well. It's an
Sir,
entire.
isn't the point A and the object in the same plane?
But you have to take an arbitrary object. The object can be anywhere. It can be above, it can be below. Okay, so you need to find
अच्छा.
out what happens to an arbitrarily placed object. You don't want to restrain where the object lies. The object could be anywhere. Okay?
Alright, sir. Alright, sir.
All right.
सर
So
ये
similarly,
प्लस और माइनस की जो सॉरी टू इंटरप्ट सर, ये प्लस और माइनस की जो डिस्टिंक्शन है ये सिर्फ हॉरिजॉन्टल प्लेन के लिए ही होती है ना? इन केस ऑफ वर्टिकल प्लेन हम ये डिस्टिंक्शन नहीं करते, तो
in
ये
case of
अबव एंड बिलो
vertical
के लिए
plane, in case of vertical plane, something that is above, you reflect it about a vertical plane, it remains above.
तो सर
Something
उसके लिए
that is
फिर
below
राइट और
remains
लेफ्ट,
below.
जो राइट और लेफ्ट की है वो सिर्फ एंटायमर्स की बेस के ऊपर होती है, राइट? के
Right or left क्या?
सर वर्टिकल प्लेन जो है कि एक ऑब्जेक्ट अगर लेफ्ट पे है तो अगर उसको उसका एंटायमर राइट साइड पे होगा
अगर मिरर प्लेन में,
यस सर।
अगर एक ऑब्जेक्ट राइट पे है वो लेफ्ट पे होगा. अगर मिरर प्लेन उस ऑब्जेक्ट के साथ पड़ा हुआ है और ऑब्जेक्ट राइट पे है तो वो लेफ्ट पे होगा उसका एंटायमर. On the other side, the reflection is made on the other side of the mirror plane. So how do mirror planes work? So if this is my mirror plane vertically placed and I have an object here, what I do, I draw a normal to the mirror plane, extend the normal to the other side. This becomes its enantiomer, the mirror image. Something that is above remains above. Something that is below remains below, but still I get the mirror image, right? So this is the action of a mirror plane.
यस सर,
Got it?
थैंक यू।
So likewise, I have 3 bar and I have 4 bar. So let's draw 4 bar and 3 bar you can draw yourself. Object here, 90 degrees rotation would land up here, followed by an inversion about this point. I get to this point. An object that is above becomes below. Okay. Now I do a 90-degree rotation about this object here. I will end up here. Then I do an inversion. I will land up here. Okay, likewise, I can create this. Okay, so this is my 4 bar point group. All right, so all of this is looking good so far. So for your convenience, I'm going to draw 3 bar. I've already drawn it on my notebook. You can practice all of this on your own. Plus. Why don't I have a 6 bar? Can anyone explain why don't I have a 6 bar? Because a 6 bar is already covered. We've already covered a 6 bar here. Okay, so it doesn't generate a new point group. So we've developed 17 point groups now, and we can do even more. Any questions?
Sir,
Mm-hmm.
isn't one bar a combination of rotation plus reflection about the plane perpendicular?
No, no. One bar is this object here. You do a 360-degree rotation, you end up here, and then you do an inversion about this point, you end up here. Above becomes below. So this is not a mirror reflection. This is a pure inversion, like
So
the two copies of my hand.
so if I rotate it by 180 degrees and then I reflect it about the mirror perpendicular to the axis, wouldn't I end up to the same place?
So I do a 180 degrees rotation.
And I reflect it about the mirror perpendicular to the axis.
2 by m. So that is, you do a two-fold rotation,
Yes.
and then, yeah, exactly, it's the same. This is the same as one bar.
Yes. So this is no new point group. It's already discussed before.
But the point is, it is a new point group. This particular operation is the same, but 2 forward slash m, 2 forward slash m would also mean that, okay, so this is one bar, but 2 forward slash m is the following, and there's a difference. This is 2 forward slash m, and this is pure one bar. And there's a difference between these point groups. This point group contains the elements 1 and 1 bar. This point group has more elements to it. All right, so there's a difference. The particular operation that you were mentioning is the same, but when we look at the point group, we have to look at all elements of the point group. Okay.
Okay.
I hope I've explained the answer to
Okay.
your question. One bar might be the same as another operation of another point group, but the point groups themselves, they are different. Okay, so now we can construct even more point groups. Now, point groups number 18 to 21, for example, they are the cyclic point groups concatenated with identity and a two-fold rotation that is perpendicular to the principal axis of rotation. Okay, so this already has an n-fold axis of rotation, right? The cyclic groups have n-fold axis of rotation. Now, if I would draw an axis of rotation which is two-fold and perpendicular to the principal axis of rotation, I can generate these extra groups. And these extra groups are of four kinds. They go with the following symbols: D2, old notation, new notation, 2, 2, 2, D3, 3, 2,
तो ये
D4,
फिर से समझा
4,
देंगे प्लीज
जी
ये जो आपने ऊपर लिखे CN into ये जो सा आपने ग्रुप लिखे आप ये फिर से समझा देंगे
अभी समझाता हूँ, एक मिनट. So let's look at this group D4 here, okay, or 422. Let me close my Gmail first. All right. Suppose I have the group C4. Let me draw the stereogram for the group C4. The group C4 has a four-fold axis of rotation that is coming out of the plane of the paper. Let me draw my object. Something that is above remains above. Now this is C4. Okay. Now what I would like to do, I would like to have this axis turned into a twofold axis of rotation. Now this twofold axis is perpendicular to the original fourfold axis of rotation that is beaming out of the plane of the paper. Okay, got it? Now what would this twofold axis of rotation do? This twofold axis of rotation will take all of these points and rotate it, twist it about this twofold axis of rotation. Something that is above goes below. This goes here. This goes here. This goes here. All right.
Sir, won't they stay in the same plane लेकिन उनकी वो images mirror हो जाएंगी क्योंकि हम two
They will not stay in the same plane. These are not, no, they're not mirror. This is not a mirror plane.
okay
Something
sir.
that is above the, I hope you're looking at my
Yes sir,
screen.
I understand. Yes sir,
Something
I
that is above,
understand.
you rotate it by 180 degree, it goes down.
Yes sir, I understand.
Okay. So this is a twofold axis. And if you observe the action of the fourfold axis of rotation and the twofold axis of rotation that is perpendicular to the original principal axis, such a new axis is called, by the way, a dihedral axis. This dihedral axis creates another dihedral axis, and this axis here is automatically created, and it's a twofold axis of rotation. That is why, that is why this new point group has a fourfold axis of rotation and two twofold axis of rotation. So its international symbol is generally written as 4, 2, 2. And the old notation is D4. It's a dihedral point group. So now we've constructed these 4 dihedral point groups. Asif, can you mute your mic, please? Okay, so these 4 dihedral point groups have been created. They have blossomed, they have come out, they have emerged from the action of an n-fold cyclic rotation, followed by a point group that comprises the identity. You do nothing to it. You keep the original n-fold rotation, or you have a two-fold rotation axis that is perpendicular to the original n-fold axis. And 4 point groups are created in this fashion. Likewise, someone asked me the question of what this thing over here means. I hope I've answered your question now. So we move on. Things get really interesting. They are interesting, they are beautiful, they are quite amazing. Mathematical group theory coming to life here. So we can also construct 4 point groups, 22 to 25, by having the C and H followed by a two-fold axis of rotation which is perpendicular to the original. And this two-fold axis of rotation now lies in the horizontal mirror plane. Okay, and the point groups that can be constructed are labeled D2H, MMM, D3H, 6 bar M2, D4H, 4/MMM, and D6H, 6/MMM. Slightly tongue twisting, but here is what it is: 22, 23, 24, 25. Okay. For example, you can always keep on constructing these stereograms. I don't want to belabor you with this. Probably I give this as a homework. 26 to 27 groups, they are formed by having the improper groups. These groups here, these three groups, one bar, 3 bar, and 4 bar, followed by a twofold axis of rotation. That is, I have one C2 2 prime acting on Sn, where n is 3 and 4. And these groups are labeled as D2D 4 bar 2m and D3D 3 bar m. Okay, so I'll probably give as a homework the construction of one of these stereograms. So we're left with 5-point groups: 28, 29, 30, 31, and 32. And these are also the easiest and also sometimes the most difficult to understand. Let me spell out what these groups are. And they are called cubic point groups. And a first student of crystallography encounters these point groups the most often. These point groups are labeled as T, international symbol 23, TH, international symbol M3, TD, international symbol 4 bar 3M, O, international symbol 432, OH, international symbol M3M. Point group number 28, 29, 30, 31, 32. The T's are generally representing tetrahedral and O represents octahedral. So let me first focus on this group. All these groups are really important. So I would like to spend 5 to 10 minutes on these groups. In the meantime, do you have any question you would like to ask me? "30 minutes of silence" means all is good or you're completely lost.
सर
But जी
सर मैं ये पूछना चाह रही थी मेरे फ़ोन
जी
की एक्चुअली बैटरी लो है तो सॉरी मैं ड्यूरिंग लेक्चर पूछ रही हूँ। सर वो मैंने 2 लेक्चर्स अटेंड नहीं किए हुए लास्ट आपके, तो मुझे यूट्यूब की रिकॉर्डिंग्स चाहिए थी, वो आप कब तक अपलोड कर देंगे?
पहले लेक्चर की रिकॉर्डिंग तो अपलोड नहीं करूंगा क्योंकि वो तो वैसे गपशप थी, लेकिन दूसरा लेक्चर की रिकॉर्डिंग अपलोड हो चुकी है मेरी वेबसाइट पर।
सर वो मुझे
जो
एक्सेस नहीं हो रही।
कोर्स की वेबसाइट पब्लिक एक्सेस है। आप मुझे ईमेल करें, आप कोर्स में रजिस्टर्ड हैं या गूगल ग्रुप्स पे रजिस्टर्ड हैं तो आपको ईमेल आ जाएगी, नहीं तो मुझे ईमेल कर दें, मैं आपको ऐड कर दूंगा।
सर मैं आपको ईमेल कर देती हूँ और मैं रजिस्टर्ड
ठीक है,
हूँ कोर्स में। चलें ठीक है, थैंक यू सर।
आप मुझे ईमेल कर दें। आप फिर आपने क्लास मिस की है ना, फिर आपने ईमेल नहीं दिया होगा अपना। All right,
ओके
so
सर
let's look at the tetrahedral, not the tetrahedral, yes, the tetrahedral group. Let me draw a cube for this. Drawing the stereographic projections of these groups is really difficult, so I will not go into the business of drawing the stereograms for this because this will get really complicated here. So I'm drawing a cube here. Hopefully this looks like a cube. Now in the 2-3 group, this point group, has the following elements. Of course, it has the identity. The identity is always there. Then it has 4 3-axes, 4 3-fold axes. Okay, so I'm putting the threefold axis in slightly bold. So those threefold axes, and there are four of them, lie along the body diagonal. So I connect this point to this point over here. This is a threefold axis of rotation. So if I were to rotate this cube about this threefold axis of rotation by 120 degrees, if the same pattern emerges, if the same crystal emerges, then I would say that this body diagonal is a threefold axis of rotation. And if I can draw four body diagonals of this kind, here is one. Let me draw the second one. Connect this point with this point. Here is my second body diagonal, a threefold axis of rotation. Let me draw the third one now. Threefold axis of rotation. I'm drawing the proper symbol with it as well. All right. So these are the four threefold axes of rotation. I could also do two threefold rotations about the same axis, which means I can have three square axes. Each one of these axes, I could either do a 120-degree rotation about them, or I could do a 240-degree rotation about each one of them. Right? So I could do a 120-degree rotation or a 240-degree rotation if the lattice or the crystal structure remains the same, it does not change, then I would say that this axis of rotation is a threefold axis of rotation. But then on top of these 9 symmetry elements, I also have twofold axes of rotation. And those twofold axes of rotation lie along the edges of the cube. So here is one of them. Here is the second of them. And here is the third of them. So I have three twofold axes of rotation as well. So if I have these 12 elements in my lattice or my crystal structure, then that lattice or crystal belongs to the 2-3 point group.
I'm sorry, once आपने दूसरा वाला
Okay.
लिखा हुआ है 4-3-2 axis. Doesn't it just come from the 4-3 axis? ये आपने अलग से 3-2 क्यों लिखा हुआ है?
Because these are 240-degree rotations.
But don't they just come from the 4-3 axis जो हमने diagram में draw की हैं? Aren't these just the part of?
Of course, they're the same, but they're new symmetry elements. They have different matrix representation. They are different symmetry elements, like the cyclic group C3 or 3 cyclic group has 3 elements, 1, 3, and 3 square. Okay, so it's a distinct symmetry operation. A 24-degree, 240-degree rotation is distinct from a 120-degree rotation. It's different. It has a different matrix. It has a different rotation operator, etc.
So let's say I have C4.
Okay, got it, man?
So let's say I have C4.
C4.
So C4 squared would be a part of C4, है ना?
Yes, but it's C4 square is a twofold rotation. So it is a distinct element in the point group. You have to look at the number of elements in the point group as well. Each element is distinct from the other.
Yes, sir. All right.
Okay, one necessitates the other, but they are distinct elements. This threefold axis of rotation necessitates the presence of this 3 square axis, but they're distinct elements, mere bhai.
All right, sir.
Okay, now I've constructed this T. If I were to add mirror planes to this T, I will get the next point group. And those mirror planes are perpendicular to these twofold axes of rotation. In other words, they are parallel to the faces of the cube. And I can draw these mirror planes here. Sorry, they're not parallel to the faces of the plane. Let me draw where these mirror planes exist. There are 6 of them. So now I'm going to talk about TH. So one is this mirror plane here. If this plane were to become a mirror plane, and this plane here were to become a mirror plane, so these are parallel to the face diagonals, and I can construct 6 kinds of mirror planes of this kind. 6 different mirror planes of this kind, right? So here are 2 of them, and the next 2 of them would be here. Here are the next 2 of them, and finally I've already drawn this, sorry.
So front to back वाला diagonal होगा.
So these 6 mirror operations, if they are added to T, they will generate additional symmetry elements. They will also generate a center of inversion. They will generate 8 6-fold axes of roto inversion. They will generate 3 mirror planes as well. So this becomes TH. Likewise, I can draw face diagonals. I can get TD through face diagonals. So what I've described here are actually TD. Sorry. What I've described here are TD. TH is simpler. TH is simply mirror planes that are, as I mentioned earlier, parallel to the faces. Sorry, I got slightly confused here. So a mirror plane here, a mirror plane here, and this mirror plane would make TH. What I've described over here is TD.
सर जो आपने purple और blue planes बनाए ये center में नहीं होंगे?
सेंटर में भी डाल सकते हैं, इधर भी डाल सकते हैं, नीचे होगा, सेंटर में भी डाल सकते हैं और इधर भी डाल सकते हैं. So these are just reflected. सेंटर में डाल लें आप, इधर भी ठीक है.
Alright sir.
Likewise, O, the O point group is the first kind of point group which has a 4-fold axis of rotation. And those 4-fold axis of rotation are along the face edges. So here is one 4-fold axis of rotation, here is another 4-fold axis, and here is the third one. So there are 4-fold axis of rotation, and each one of these 4-fold axis of rotation is also a 4-cube rotation. Okay. And in O, we additionally have two-fold axes of rotations, which are along the face diagonal. So if I draw face diagonal, this is a face diagonal. This is a two-fold axis of rotation here. And there are 6 face diagonals. Here are 2 of them. Here are 2 of them.
सर आप
Here
ओ
are
फिर से समझा देंगे
जी
ओ फिर से समझा
जी
देंगे प्लीज
अच्छा एक मिनट पहले बना लूं एक it becomes a complicated figure here.
यस यस
In the octahedral group O, which is represented by 432 in the international notation, I have 4-fold axis of rotation. Each edge of the cube is a 4-fold axis of rotation. You rotate by 90 degrees, you get the same structure. You can rotate it by 270 degrees as well. So each edge of the cube is a 4-fold axis of rotation, and it's a 4-cube axis of rotation as well at the same time. In addition to that, each face, you draw a diagonal on the face of the cube. This diagonal becomes a 2-fold axis of rotation as well. You rotate the entire lattice or the structure through 180 degrees about this face diagonal. You preserve the symmetry, you get the identical in equivalent structure or lattice.
सर हमने सेकंड क्लास में ये पढ़ा था कि जौन सी भी हमारी रोटेशंस होती हैं दे शुड बी सच कि जब आप रोटेट करो आप ओरिजिनल इमेज और नई इमेज में कोई फ़र्क ना बता सको लेकिन अब आप यहाँ पे ये बता रहे हैं कि हम एज पे रोटेट कर रहे हैं तो वो तो स्पेस में पोजीशन ही उस क्यूब की चेंज हो चुकी है अब उस रोटेशन की वजह
लेकिन
से
we have a 3-dimensional pattern. We have an object that is filling up the entire space. This lattice is filling up the entire space. Okay, so everything holds true here. If I take a cube, okay, and
Yes,
I
sir.
rotate it by 90 degrees. So let's talk about a crystal, morphologically a crystal that is a solid finite macroscopic object, a cube. Okay. Now, if I rotate it by 90 degrees, of course, I'm changing the position of the cube. I land it somewhere else. But if I ignore the spatial translation, the object is
फिर
still
तो
the same.
ज़रूर सर यस सर फिर तो
Right?
होगा
So we haven't yet considered translational operations. The macroscopically, the object remains the same. And that is the beauty of point groups. Point groups deal with the external morphology or the macroscopic symmetry. They don't take into account any translation symmetry operations, and there exist translation symmetry operations. When we discuss crystal structure, we're going to talk about them. There are screw operations, glide operations. We're not talking about them. We're talking about the morphology of the crystal. If we are inside the crystal, this 3-dimensional network extends to infinity. So everything that is rotating, you can find it in its neighboring adjacent space as well. Okay, we have space filling patterns here. Okay, I hope
Understood.
I've
Yes.
answered your question. So these are there are 24 elements in O. The original ones followed by 4-fold axis of rotation and 4-cube axis of rotation and 6 face diagonals as well. And if you have O and you link it up with the mirror plane, you will get OH. OH has 48 elements. And this is the most symmetric of all the point groups. So this covers my discussion on point groups.
So total 32 नहीं?
So this is the 32nd point group, which has 48 elements in it.
Okay, sir.
All right. Now, any questions about all of this? And I just want to take 3 or 4 minutes extra to talk about the significance of point groups.
सर मॉलिक्यूलर
All
सिमेट्री का जो कोर्स हमने पढ़ा था तो आई डोंट नो कि क्रिस्टल सिमेट्री में वो फॉलो करेंगे कि नहीं करेंगे, उसमें 2-3 और पॉइंट ग्रुप्स थे जो हाई सिमेट्री थे। एक IH था और फिर C infinity और D infinity भी थे जो लीनियर मॉलिक्यूल्स के लिए होते थे। तो आर दे एप्लीकेबल या फिर उनका भी यहाँ पे रिलेशन है?
So here we're talking about three-dimensional structures. So linear molecules, they are one-dimensional.
ऑलराइट सर, लेकिन जो
So here
IH
we're
था
talking
वो
about three-dimensional.
जो IH था वो 3 डायमेंशनल था और इट वाज समथिंग लाइक अ बकी बॉल, उस तरह का मिलता जुलता स्ट्रक्चर था इसका।
So there are 2 points we would like to consider. We would like to consider space filling groups which do not leave any voids. So there are slight distinctions between original molecules that are free floating and crystals. But even in crystallographic symmetry, there are 32 point groups.
ऑलराइट सर, थैंक यू।
All right, so what is the significance of point groups? If you look at the 27 point groups before the cubic point groups, all of them in all of them, the symmetry elements pass through a single point, and there is a principal axis of rotation. In the 5 cubic point groups, there is no one principal axis of rotation. Okay, there are multiple axes of rotation, and it's possible that the axes of rotation do not pass through a single point. There's no principal axis of rotation in the cubic point groups, in short. Now, all of these 32 point groups, they deal with the external morphology of the crystal. You take a crystal in a macroscopic world, look at its form, look at its shape. You can assign its external morphology to one of these 32 point groups. So even if you didn't know atomic structure, even if you didn't know that these crystals were comprised of atoms, that there's an internal structure to these crystals, you could look at the crystals. Gemology and gemstones and minerals have been there for millennia. So you took a crystal of a mineral, look at it, you can assign its external morphology to one of these 32 point groups. You can rotate it in different ways, and it must fall into one of these 32 point groups. Okay.
Sir, so what we studied were groups which have like a few rules to them, ki identity or inverses, so etc. But like when we talk about real life, actual structures may or may not follow these rules. So, so how can we say कि these would apply to all
Uh,
crystals?
they apply to all crystals. Any crystal, if it has no symmetry at all, it's the simplest point group 1. If a crystal is centrosymmetric, it belongs to the point group 1 bar. So you can assign any crystal to one of these 32 point groups.
All right, sir.
Okay. If it doesn't have any symmetry, it gets lumped into the point group 1 identity. It's possible to have a crystal of that kind. Okay.
Yes, sir.
The crystals have faces. If you draw a crystal, let me draw a crystal here. Just arbitrarily, I don't really. So if I look at this crystal, I am not drawing a good diagram here, but this crystal must belong to one of the 32 point groups. It could have a mirror plane. It could have a mirror plane that is horizontal, vertical. It could have a two-fold axis of rotation, a three-fold axis of rotation, and so on. So it must belong to one of the 32 point groups. Okay. So external morphology is determined by the point groups. And it is totally divested. It is totally independent of the atomic structure. You don't care what the atomic structure is. You don't care about the periodicity of the crystal, of the atoms inside the crystal. Lattices can also be lumped into one of the 32 point groups. Crystal structures, if you ignore the translational symmetry elements, they can also be lumped into one of the 32 point groups. Now, these point groups impose certain constraints on the lattices. And as a result of these constraints, there are only 7 kinds of lattices. And these lattices are called crystal systems. Now, in the next lecture, what we would like to do is we would like to look at a point group and see what constraints does it impose on the lattice. And there's a repeating unit in the lattice that is called the unit cell. What constraints does the point group impose on the shape of the unit cell? And it turns out that only 7 kinds of shapes are possible, which are called the crystal systems. They are triclinic, monoclinic, orthorhombic, tetragonal, cubic, hexagonal, and trigonal or rhombohedral. Only 7 kinds of crystal systems are possible, and they arise because of the point groups. Now, just before I finish this class, if you look at my screen over here, you will observe that the point groups, for example, if I look at the tetragonal point group, the tetragonal crystal system, it comprises the point groups 4, 4 bar, 4/m, 422, 4 4 bar 2m, and 4/m. These point groups, all of these point groups have a 4-fold axis of rotation or a 4 bar axis of rotation, all of them. And any such lattice which has a 4-fold or a 4 bar axis of rotation imposes a constraint on the size of the unit cell. That is, 2 sides have to be equal, could be unequal to the third side, and all 3 angles have to be 90 degrees. This is a constraint on the unit cell. So what we're going to learn we've developed point groups today. I'll try to construct a homework. We've developed the point groups. Now what we would like to do is we would like to see how we develop the crystal systems out of the point groups. Now, when you learn a solid state physics for the first time, most instructors would just start introducing and just lay out the 7 crystal systems, cubic, orthogonal, tetragonal, etc., without recourse to the symmetry elements and the point groups. We have done a more systematic approach. We've introduced the point groups. We're going to talk about the crystal systems. We're going to center the crystal systems. And then finally, we're going to talk about space groups, which is the real glory of crystallography, so that we can have a handle on how do we describe crystal structures in their full glory, in their full beauty, and with complete knowledge of the different symmetry elements. All right, so I'll try to post a homework this week. The homeworks, as you know, I'm going to follow an honor code. Uh, you can consult any book, you can, but don't plagiarize or copy. You're welcome to collaborate, but come up with your own solutions. And I will work on the premise that there will be no copying, there will be no plagiarism. So this is how we're going to conduct this course. All right, so thank you very much, my friends. Sorry if I take too long. Teaching on the whiteboard is slightly different from teaching on a blackboard in a real setting, but I'm
सर
learning.
मैंने आप
So
सर मैंने आपको चैट में
जी
एक मैसेज भेजा है, वो देख लेंगे प्लीज़ मीटिंग एंड करने से पहले।
ठीक है, ठीक है. अच्छा, Bilal, you stay over. The rest they can leave. Thank you very much, friends.